Hi, I'm Mr. V, and this is I'm going to be talking about section 2 of the illustrative mathematics, congruence for quadrilaterals. And if you went to your Google Classroom and you logged in, you could find this Desmos activity. All of our activities today are on Desmos, except for I'm going to go through a couple of homework problems from the previous night. Here's one. It says select all quadrilaterals for which a diagonal is also a line of symmetry. And they give you a trapezoid. The general trapezoid has one pair of parallel sides. So it could be like this. These two sides are parallel. And then you could make this one extra long. Two sides are parallel. A isosceles trapezoid, which has one pair of parallel sides, again, and the legs are congruent like this. A parallelogram, which I'm going to draw nice and long, and the sides do not have to be 90-degree angles, but these two opposite sides are parallel by definition in a parallelogram. And rhombus. Rhombus is an equilateral quadrilateral, so all four sides are the same, like this. And then a rectangle, and finally a square. And what we're asked is, are there any lines of symmetry by a diagonal? So I'll draw the diagonals on all of these. I'll put at least one of the diagonals on each of these. And if you were doing this on a test, you might want to try to draw the diagonals and draw the picture just to verify for yourself that this works or it doesn't work. When you reflect across a line of symmetry, you're going to go an equal distance on either side, and it has to be perpendicular to that line. So if I go from this point, it has to be this distance perpendicular to this on the other side, in which case this would be the line of symmetry. It does not match up. The first one does not match. The second one, I'm going to go from this point perpendicular to the line of symmetry, which would be my reflection line, and go across. This would make a kite. This does not work up either. For a parallelogram, if I go perpendicular to the line of symmetry and across it, again, a kite. It does not necessarily make it so. Now, a rhombus, if I take this line, if I take this point and reflect it across this line, it ends up where I'm wanting to. Same with the other diagonal. This one works. And since a square is a rhombus, a square would also work. A rectangle would not work. If I'm going to reflect this line across this at a perpendicular, it ends up being like that. So this is not a reflection. Second thing we did was we looked at this problem. This is one that has appeared several times. And so I'm suggesting it might be on a test somewhere. I don't know if that's true or not, but we will find out on, this is the last section of this unit, so we'll be testing on this unit very shortly. Segment DB is congruent to segment AC. Segment DB is congruent to segment AC. That is not enough, or BC. That is, this would define a isosceles triangle. We're trying to see if this triangle DBC is isosceles with this little bit of information that's added to this given information. The second one, it says segment AB is congruent to segment BD. AB is congruent to segment. This is not enough information. Third is that these two angles here are congruent. And if you look in the assessments, it will say that this is wrong, but I'm telling you this is correct by the side-to-side angle, sometimes triangle congruence theorem. It's true if this angle that is given is obtuse, and there's no way to make this angle acute to where they're both congruent. They'll have to add up to at least to be 90 degrees and with them being congruent, and these will probably be longer. And that would be if this point were on the segment DC. So if you marked it true, it is true. If you marked it false, you would get credit for it in assessments, but I want you to know that this is true. Angle ADC, ADC, and ACD, not enough information. All that tells me is that the large triangle is congruent. If I were to draw a counterexample, here's the large triangle, and saying these angles are congruent, I could still put this other point anywhere in here, make it not. So it doesn't say that these angles have to be congruent or anything. AB is an angle bisector. This would be by the side angle side. These two triangles are congruent. And yes, that is enough information. And finally, to say that the two triangles are congruent, yes, by CP/CTC, the corresponding parts of the congruent triangles are congruent. So that would work as well. In today's lesson, we went through a number of different type of activities. We're looking at quadrilaterals, congruence in quadrilaterals. And you can use rigid motion transformations to prove they are congruent. You could write conjectures about quadrilateral congruence. That was the goal for the day. And it's kind of a light day as far as the amount of work that is required compared to some of the things that we've been doing recently. So if you're given a quadrilateral, I'm going to put this on the student view. A quadrilateral is a parallelogram. What must be true, what could be true, what definitely can't be true. You should try doing this on your own. For the activity, we actually went through this in class. I made a list of all of the comments that students made. Of course, we know that opposite sides must be parallel. That's the definition. We've proved that opposite sides must be congruent, opposite angles must be congruent, and that the diagonals bisect each other. Now, diagonals could be congruent. And if they are congruent, you're going to have a rectangle. And I can show you that with GeoGebra. I should do that. GeoGebra, and we'll do this with the classic GeoGebra. So if I start off with a segment, and we know that the in a parallelogram, the diagonals bisect each other. So I'm going to mark this as the center point. So it's got to go through the center point of this segment. Now our second line, if it's going to be congruent to this second segment, is going to be congruent to this segment, I should be able to make it into a circle because the diameters of a circle will be congruent. So I'll do it like this, and I'll draw a line through it using my line tool, going through the center up to the circle. And here we have an intersection, making this a quadrilateral. And I want to do intersection. And if I make this into a polygon, you can see that this is going to be a rectangle. When I do a drag test, it stays a rectangle. I move this point around. For these two diagonals to be congruent, for the two diagonals to be the same length, both of them are diameters of this circle, this will always be a rectangle. That's an interesting property. One person said in our list, they said that the diagonals would be perpendicular. And I can construct that too to see this would be a rhombus if the diagonals are perpendicular. I know that because if I look at my midpoint, it has to go through the midpoint. And for it to be perpendicular, I'll construct a perpendicular line through the midpoint. It's perpendicular to this line. And now for it to be a parallelogram, there's a number of ways of doing this. I'll do it with a segment. I'll draw a segment from here to here. Notice that this segment also has to extend to this other side. Now, to go through this point, to be a parallelogram, the opposite sides have to be parallel. So it'll be parallel to this through this point, parallel to this through this point. And when I draw my intersection and my my figure here, polygon, you can see that this is going to be a rhombus. All four sides are congruent and the things are perpendicular. So it's a special case for a parallelogram, but special case for parallelogram that you can move this around. Now, let's see. Some other comments. It could be true that they're all right angles, in which case it'd be a rectangle. It could be a square. It doesn't have to be a square, but it could be a square. It could be a rectangle, or it could be a rhombus. What can't be true, can't be a trapezoid, can't be an isosceles trapezoid, can't be a kite or a dart. That's the family of trapezium. It can't be a circle, can't be a hexagon. It can't be a three-dimensional figure. Those are called hedron, polyhedron instead of polygon. And it can't be such that the diagonals do not bisect each other. Someone said it's possible that the diagonals could bisect each other, and I have an argument with that because we know that for it to be a parallelogram, the diagonals must bisect each other, and if the diagonals bisect each other, it can't be anything but a parallelogram. Now, one person made the comment about symmetry. They said that it's going to have symmetry, and I asked the question to the class, does this figure have symmetry? And some people tried it. Some people looked at it and tried it. And this is our parallelogram. And I need to copy this. Copy. So in our parallelogram, if you tried to rotate it, and I could do this on GeoGebra just as well, to show you what it looks like. So to do this, I will again I'm going to do it this way, draw a segment, put its midpoint, this segment, it's got to bisect each other. So to find my other segment, I'm going to draw a circle. This would be an interesting way to construct and I'll do a line going through 0. An interesting way of constructing a parallelogram. I should do it this way. Hang on just a second. Go backward. Do my circle from here to somewhere on the thing, and I'll draw a line through this point. That way I can make it dynamic and make it move. Where these two intersect, I'll draw it, and the question is, does this have rotational symmetry? That's what we're looking at. So I have my parallelogram. The diagonals bisect each other. Both of these are radii. And when I drag it, you can see I can drag this around. I can make this different. I can drag this point, make this bigger or wider, put it anywhere. And it's still going to be a parallelogram. And the question is, does it have symmetry? I'm going to look at this from a different standpoint. I'm going to see if it has reflective symmetry. So I'll look at the diagonals and see if I can reflect this particular triangle across the diagonal and have it make and meet up with this other parallelogram. And I'll color this one. Let's see, I won't color this one at all. I'll color this one. Let's color it green. Now, when I reflect this across the diagonal, so I reflect this across this line, you can see it makes a kite. It doesn't necessarily have, in fact, parallelograms do not have reflective symmetry unless it's a square or a rhombus. If it were a rhombus, it could also have reflective symmetry. So these two match up. But it does not guarantee. So it may, but it does not have to have reflective symmetry. Now, what about the rotational symmetry? So if I look at this figure and I say, can I rotate it around this point? And when we do that, let's just do it here. Rotate this figure around this point by 180 degrees, we get it matches up perfectly. And if we do a drag test, you will see that it's going to pass the drag test. Anytime you move it, it's going to retain its properties. It does have symmetry, but it's rotational symmetry, and reflective symmetry only works in some cases. Now, that's what we learned from this bell work. Next, we looked at floppy quadrilaterals, and you can read this. This woman is saying, well, we did all these things with shortcuts for triangles. Instead of measuring all 6 parts that we know about triangles, the 3 angles and the 3 sides, we could use a shortcut to prove they are congruent. I wonder if there's any shortcuts for quadrilaterals, specifically for parallelograms. So if 2 parallelograms have 4 pair of congruent sides, do they have to be congruent? You think about this, you answer it, and then you look over here, the answer is no. One could be squished down. Here we have 4 pairs of sides that are congruent to the corresponding 4 pairs of sides. Opposite sides are congruent. This is a parallelogram, and these are not congruent parallelograms. Side, 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 side is not a valid reason for looking at valid reason for proving parallelograms are congruent. Yet here we have In parallelogram ABCD and EFGH, AB is congruent to EF, BC is congruent to FG, and angle ABC is congruent to EFG. Are they congruent? And now there's like 20 minutes to explain this and to look at it. I'd like to look at it here. So if I have a parallelogram, and the parallelogram means that both pair of opposite sides are parallel, both pair of opposite sides are congruent. That's something that we proved about parallelograms. So this side is congruent to this one is congruent to this one. Both pair of opposite angles are congruent, and adjacent angles must be supplementary. So these two angles, these same side interior angles, have to be add to 180. Same with these two. Now, with this in mind, and let me just copy this over. So with this in mind, I'm going to draw EFGH. We're told that EF is the same length as AB. So these are congruent. And then we have this angle is congruent to the angle, and this side is congruent to this side, to FG. The question I guess you really want to ask yourself is, where does H go, and how do you know it? One way of looking at this, which some students did, was to, I'm going to just change this to a different color, make this a nice bright. So here we have pink. This triangle is congruent to this one by the side angle side triangle congruence theorem. The question is, where does D go? Does it go to the same place as H? Because so far I've got three parts of this. And I want to point out to you that in a parallelogram, if you have three vertices that line up, you must have a fourth. So these three vertices are guaranteed, and this fourth one has to. Why? Because opposite sides are congruent, like this, and opposite angles are congruent. Adjacent angles are supplementary, so they have to be. So the side, angle, side, parallelogram congruence theorem. It is valid. It does work. And we explored this. We talked about it a little bit in the synthesis. I was looking for people who would break this into triangles, use rigid motion transformations to move one onto the other. And what happens if they coincide? What happens? Is it possible that they would not line up, that H and D? If three of the vertices line up in a parallelogram, the fourth one must as well. In page 10, you were supposed to come up with your own shortcuts. Now, parallelograms, we've proved things about parallelograms. We've also proved things comparing two triangles, the shortcuts to prove one triangle is congruent to another. And the task was to come up with your own criteria that's enough to be sure that two parallelograms are congruent. And I would give you lots and lots of time, 15 minutes to talk about this. You could record your work here. If you wanted to do more, you could do more by going on with this. Now, I'm going to point out some of the theorems that some students had. Somebody said we could do angle, side, angle, because we had a side, angle, side, and with the triangles, we had a angle, side, angle. So if we look at the angle, side, angle, let's just say I take this angle right here, and this angle, they must be congruent, and this side. Does this guarantee that I'm going to get the same quadrilateral here if this is E, F, and G? To get to G, I could put it, I know that the opposite angles are going to be congruent, so I could put it way over here. And I know that the opposite sides will be congruent, so this side has to be congruent to this. But can you see I can move it anywhere? This doesn't work. This is not valid. Someone said, why don't you try the angle, angle, side? Maybe that would work. And again, we get the same kind of thing. If I have an angle here and another angle here, and this side length is congruent to the one up above, again, I can move this third side anywhere. This does not work. Two people came up with different ones that worked. What about the side, side angle? I told you that the side, angle, side works. What if I gave you the side, and this angle? Would that work? Well, it does. It does for a specific reason, that the adjacent angles must be supplementary. And the opposite angles must be congruent. So this angle has to be equal to this one, and this one has to be equal to this, which means then my opposite sides will end up in one place and one place only. And so this is valid. And I think there was one more that was offered, but I don't remember what that one was. For the cool down, there was an instruction here, side, rectangle congruence theorem. It says if we know two corresponding pairs of adjacent sides in a rectangle are congruent, then the rectangles must be congruent. And you're supposed to explain why. And folks, this would be the side angle side theorem but it's a side for rectangles, but you're just given that the angle is 90 degrees. And that's it. Good luck and success.